So I'll begin with a word of prayer here once I get back. Heavenly Father, we thank you for this day. I thank you for these students. Just ask you to just bless our work today. Help us to understand a little bit more about your creation. And again, I just pray that you'd encourage these students to just do their best each day, Lord, on this class for your glory. In your name I pray, Lord Jesus. Amen. Okay, so how do we graph such a thing? I think the way to do it is to go, okay, so this is like y equals 1 over x squared, right? It's like the volcano graph. We take that, and then you can shift that thing 2 units to the right, yeah. So right 2. And then we take that, and we shift up 3 units, right? And so I'll draw a picture for each one of them steps. So my original one up. So I basically have the volcano graph to start with, right? Then I shift right through 2 units. And then I shift up. But let me, to do a good job for the volcano graph, it's always a good practice to put in the vertical and the horizontal asymptotes, right? So like the vertical asymptote is the y-axis, the horizontal asymptote is the x-axis. Then when you shift right 2, then the vertical asymptote is now at 2, right? Final move, the vertical asymptote stays at 2. But the horizontal asymptote is up here at 3. And so the graph looks something like that. So, okay. So there you go. This is the graph of y equals 3. Well, it's right up above there, right? That's the graph. So, any questions about this? Okay, so this is just a warm-up, but I'm going to use this example to further illustrate some of the terminologies I'm going to introduce to you guys today, okay? So there's 3 major qualitative terms I want to try to unwrap for you today, and then once we're done with that, we're going to turn to the problem of constructing new functions from old, or what are called function operations, all right? So, but let's finish the graphing part of the lecture first. So here we go. We have even function. We have odd functions. And we also have a discontinuous function. So I want to try to illustrate those and give you some kind of definition. So I can give you a concrete definition of even and odd. An even function is one for which f of minus x is equal to f of x. An odd function is one for which f of minus x is equal to minus f of x. And this is, of course, both of these is for each x in the domain, right? So for each x in the domain, if you have f of minus x equals to f of x, it's said to be an even function. If for each x in the domain you have f of minus x is equal to minus f of x, it's said to be an odd function. And what would we mean by discontinuous function? So, I mean, to carefully define discontinuous function, that's part of a discussion in calculus. But you know, for our current purposes, we can just be sort of a little bit more intuitive about the description of that. And I can just say a discontinuous function is one which has a jump in the graph. Jump in its graph, okay? So like, all right, so let's look at this. Example 2. Let's look at an example. So example 2, we might have y equals to x squared. So x squared is my f of x, right? So what's the graph look like there? This is a what? A parabola, right? It's one of our standard examples. We know this. So there you go. There's your graph. Y equals x squared. Is this an even function? Let's check it. Let's check it, right? So to check that, let's look at f of minus x. What's it equal to? That's equal to minus parentheses squared, right? Minus x squared. Now when you square that, minus times minus gives you plus, right? So this is just equal to x squared, which of course is equal to f of x, right? So in fact, this is an even function, right? Right, it's an even function. Okay? Now, we want to talk about this in other terms, right? Yes, it's an even function, but there's another thing we can say about it in terms of symmetry. All right, so what do I mean by symmetry? Symmetry of an object generally refers to the object being unchanged when you take some kind of transformation on it, right? So like here, the symmetry I have in mind is symmetry. It's like a mirroring, right? You can see that you mirror the graph over the y-axis. You're back to it again. Let me put it in different terms. If I have this point, a comma b, right? I also have another point over here, a partner point, minus a comma b, right? Like that. That's the symmetry. Like if I can swap those points, those kind of pairs of points, and I still have the same picture. Just to get to the point here, it's symmetric with respect to the y-axis, right? You can reflect the graph over the y-axis and you still have the same graph. That's the symmetry property for an even function. Are we good? Okay. Example 3. Suppose we have, we're going to look at y equals to f of x. This time f of x is going to be x cubed minus x. All right. So how do you graph x cubed minus x? So let me show you. So what we're really looking at is y is equal to x squared, excuse me, x times x squared minus 1, yeah? Which is x times x plus 1 times x minus 1. So from that I can see that this has x-intercepts of 0, 1, 0, minus 1, and 1. And so I can draw the graph like so. I've got my x-intercepts of here, here, and here. 0, minus 1, 0, and 1. And so the graph here looks something like that. This is y equals x cubed minus x. Do you guys like time travel? Because that's what we're doing right now. This is actually the topic for like next Monday. Okay, Monday I'll probably be talking about how to graph polynomials, maybe even Friday if we're lucky. But so like to graph a polynomial, what you want to do is like figure out where it's 0. You put those as your x-intercepts and you kind of go from there, right? I haven't really explained this yet, I'm just doing it. The reason I'm doing it is I want us to have a nice example of a function, right? Is this function even? Is it odd? What's the deal? Let's try it out. What is f of minus x here? F of minus x is what? It is minus x quantity cubed minus a minus x, right? So I just put in minus x in the place of x. What is minus x cubed though? So what you got here is minus x cubed plus x, right? Minus minus is a plus, but notice then you can factor out a minus here, right? We have minus parentheses x cubed minus x, which is minus f of x. In other words, we can calculate that f of minus x is equal to minus f of x. That means this function is what? This is odd. This is an odd function. Okay? Now, is this function symmetric with respect to the y-axis? It's not, right? If you reflect this shape across the y-axis, what do you get? You get something else, right? Something different. You don't get the same graph again. What is going on here, though, is that if you look at the point, let's say a comma b, right? What's the corresponding partner point? It's kind of like down here, you know? It's minus a minus b. So like there's these sort of pairings of points. And so this when your graph has a property like this, when every point a comma b comes with a partner point minus a comma minus b, this is called symmetry with respect to the origin. Or people will say you can reflect this graph through the origin. Right? So this is symmetric with respect to the origin. That's the language. Symmetric with respect to origin. Now, as a student, I always found this language kind of odd, but it's the language people use, right? So it's symmetric with respect to the origin. Odd functions are symmetric with respect to the origin. Yes, sir?
If this is like a question like this is asked in the test, would we need to write the f of x equation on the bottom, or could we recognize that all as being odd function?
Oh, well, I think that depends on the question. I might say, you know, give an algebraic argument. If I said give an algebraic argument that the function is even or odd, then an algebraic argument would be what I wrote here, or what I wrote here, right? If I said give a graphical argument, you know, I might not say give a graph. I don't know how you give a graphical argument. I might say determine from the graph is the function even or odd. And there I'm more or less asking a yes/no kind of question. Like even, odd would be the answer. And because yeah, I could make you write down a sentence, well, for every point a comma b, there's also the point a minus a comma b, therefore it's even, but I don't do that. I just say, you could write a sentence, this function, the graph who's given, is even because you can see that the function is symmetric with respect to the y-axis. Or you could say you get the same shape when you're reflected over the y-axis, so it's an even function, right?
And is that a second part?
So it depends on how the question's asked.
Okay.
Yeah.
And then when it says y equals f of x equals x cubed minus x,
Uh-huh.
that's substituted there for.
So what's going on there? This is really the definition. Right here, this is really just the definition. This is defining f. Truthfully, that's defining f of x. So, you know, here I just put it on the other side. I mean, like, don't read too much into it. It's,
Yeah.
I could.
Why did you factor out x on there?
Well, if you remember from class next Monday, we discussed that if we factor the polynomial, then you can see the zeros of the polynomial, and then those are places where it intersects the x-axis and so forth. So that's the time travel. Like, I haven't explained that yet. I just did it. I did it so we could have a more interesting graph to look at. I could have just graphed x cubed. That's on your sheet, right? But I thought, let's make it more interesting. So that's even, that's odd. How about this one? Is this function even? Is it, well, not this one, this one. Focus, let me focus our attention here. This right here, even, odd, what do you think? So if it's even, right, if I pick this point, like a comma b, whatever that is, there has to also be the corresponding point over here, but it's not there, right? Like this function, if you reflect it over the y-axis, you get a new graph. You don't get the same graph again, right? And if you reflect this through the origin, you don't get the same graph either. This, our example 1, is not even or odd. Okay, so there are graphs. This is neither even nor odd. Neither even nor odd. Right? Yeah? Okay, so some functions are even, some functions are odd. Many functions are neither even nor odd. Let's look at an example of a discontinuous function. I'm going to erase this business over here if that's okay with you guys. Any questions? No? Just jump in if you got a question. By the way, I should be getting, over the next few lectures, I think I will be well ahead of our schedule. So if that actually happens, there's hope that we won't have class next Wednesday, if that's okay with you guys. Okay. Yeah. So, or there may be a class period which is kind of optional, like I'll just hold a help session or something like that. So I might be here, but you might not have to be, kind of thing. Or maybe I'll just post a video. I don't know. We'll make a decision for sure on Monday, right? But I don't anticipate there being a formal class next Wednesday. Let's say that, okay? All right, so example 4. Now this one's really, really different. This is called the ceiling function. And this is a notation for it. So ceiling function of x, it's equal to, the next integer, I can't spell integer. That seems wrong, integer. No, it's okay, my spelling. Integer greater than or equal to x, okay? So let me just give you some examples. So what's the greatest integer of 1.1? What's the greatest integer of 0.5? What's the greatest integer of minus 1.2? All right. So it's the next integer greater than or equal to x. What is an integer? No idea. So this z, 0 plus or minus 1 plus or minus 2, These guys are the integers. They're whole numbers or they're negatives and also 0. You might, why is that z? Well, it's because once upon a time Germans were really important and stuff, and they controlled mathematics for the most part. I mean, they was the center for mathematics in the world was in Germany in Göttingen, and Zahlen is number in German, so it's from that time. So if you're wondering, no one cares. Anyway, so 2, 1. What's the next integer larger than minus 1.2? Think about the number line. So here's minus 1.2. Here's minus 1. Here's 0. Here's 1. Here's 2, right? It's minus 1, right? And then if I do 3, what's the integer greater than or equal to 3? Greater than or equal to, right? So it's just 3. Okay, so this is the ceiling function, all right? What's its graph look like? It's like a staircase, that's right. So, so it's 0, and then, let's see here, open, something like that. So the open circles on the left of each one, all right? So this is 1, 2, 3, minus 1, minus 2, minus 3. All right, here you go. This is the ceiling, the graph of the ceiling function. This is pretty far divorced from anything else we've done this semester, right? This is a really weird example. It's not like x squared or x cubed or the square root of x or the cube root of x or the absolute value of x. Any of our lovely algebraically defined functions, right? Because this example really is from something else. It's from number theory, okay, which is a different part of mathematics. This might fit better in a discrete mathematics course, but it's a good example for us here because it gives us plenty of examples of what are called discontinuities, right? So there's a discontinuity in the graph here where? At each integer, right? There's a jump. See it? Jump, jump, jump. So like roughly speaking, discontinuity of a function is when, as you're graphing it, you have to take your pen and like lift it up in order to get to the next part. You know, I can't just continuously graph this. I can't help but like take the marker up, get to the next thing, you know? Discontinuous. All right, before we leave this example, one other thought. What's the domain and what's the domain of the ceiling function? What's the range of the ceiling function? I think that's a good exercise for us. Yep.
Isn't the domain just all the numbers?
The domain is all real numbers. Very good, because I didn't skip a beat. I mean, every x, you can always round up to the next integer, right? Or if it's an integer, you just keep that integer, right? So yeah, you can do that for any number. So the domain is everything. How about the range? The range is kind of weird, isn't it? What are the y values that the graph takes? Just what? It's 0, it's 1, it's -1, it's exactly this set, right? The range is the integers. So anyway, it's kind of a funny example, but there we go. We good? I hope so. All right, so that's pretty much all I have to say about special kinds of graphs. We can talk about even graphs, we can talk about odd graphs, discontinuities. There's one other example I should maybe do. Let's do one more example on this stuff, and then we'll go on to the next set of topics here. A fun example is, you guys ever do like Build-A-Bear? You guys know about the Build-A-Bear? Overpriced stuffed animals. Yes, here. Crazy overpriced. So here's a build a function. All right, so you're given, you know, y equals f of x below. So let's suppose that you have, you know, y equals the square root of x, right? So I'm saying that that's f of x, okay? Just for the sake of discussion. So what I want to ask you guys is part A, find g of x even, which extends f. And then part B, find h of x odd, which extends f. In other words, I'm saying complete the graph that's given to a graph which is either even or odd. Right? So like, I can do it graphically pretty quickly, and then we'll think about the formula, okay? So like, we have this, right? How do you continue that in order to get an even graph? You just reflect it, right? Just reflect it across the y-axis like this, right? So this, what I've pictured, would be y equals g of x that's even. You see that? This would be an even graph. So I just reflect the square root across. What would it look like if I wanted to make an odd graph? Right, I'm given the square root, right? I want to make a new graph which is odd. Where should I need to reflect through the origin, right? So like the part I'll add in red. It would just be like this, yeah? So this would make y equals h of x. And this graph is odd. So that's graphically how you could, if you have like half of a function, you can make up the other half if you know also the function's even or odd, you know, in this sense. This is called extending a function. Can you guys give me the formulas for these in terms of case-wise defined things? Let's try it out. I'll do the easy part. So the easy part is square root of x for x greater than or equal to 0. That was given. Square root of x for x greater than or equal to 0. That was given. But what about x less than 0? What's the formula for x less than 0? Can you guys tell me? I'll write it in blue here in a second. What's the formula here that we should put? What do you guys think? Any ideas?
For the first one.
Uh-huh. So last class told me for the first one minus the square root of x. What do you guys think? Is that right or wrong? What about that one? Is that right or wrong? It's wrong, right? I mean correct? I mean incorrect? This square root of negative x is what we want there, right? Because otherwise you can't put in a negative number, right? Now that formula makes sense because if we put in like minus 2, or put in minus 4, right? What is the square root of minus minus 4? No, not square root of 4, which is 2, right? So like putting a minus here makes this formula make sense when x is negative. And so, you know, there's a point here, 4, 2, and it's reflected over to this other point, minus 4, 2, right? This is an even graph in that sense, so that's the formula in that case. How about the second? How part B? What would I? So I hear, yeah, minus the square root of minus x is what we want. So what that does, what that formula does, is first of all, minus the square root of minus x flips you over to here, and then when you do minus again, you turn that over, like that. So that's why this red graph right here, this red piece here is y equals to minus the square root of minus x for what it's worth. So anyway, I think these are a little bit more adventurous and interesting, right? If I just give you a graph and say, is it even or odd? It's kind of a silly question. This is a little bit more, you know, challenging. Given a graph, how do you extend it to get an even or an odd graph? You know? All right, so next topic. Operations on functions. a.k.a. new functions. From old. So I want to explain to you how if you give me a pair of functions, let's say f and g, so given functions f and g, right, we can construct new functions. Let's say f plus g, f minus g, f times, let's say c times a function. C is a number, okay? cf, f times g, f over g, and last but certainly not least, f composed with g. These are all new functions that we can define. Let me give you the names, all right, just the names. This is the sum, difference. This is a scalar multiple, the scalar multiple of f. Here you're looking at the product, right? So the sum of the functions, the difference of the functions, a scalar multiple of the function, a product of the functions. What do you think f over g is called? Yeah, a quotient of the functions. And then finally last here, This is called the composite of f with g. And just to add a little bit more nuance here, where g is the inside function. Right? In this case, f is the outside function. We have inside function, we have outside function, right? Now, up till now, I'm just name calling. I'm just giving them names, right? How do we actually define these things? Let's do it. I'll do it right here. It's pretty simple. We define it in terms of a formula, right? So here's the formula. If I have f plus g, and I evaluate it at x, how do you define that? Well, it's just f of x plus g of x. That's the way the new function f plus g works. F minus g of x, guess what? F of x minus g of x. That's how that works. Nothing too surprising so far, right? A constant times a function. How is that defined? It's just the constant times the function, its value at x. All right. How about the product? Fg of x is equal to f of x times g of x. That's the product of the functions. F over g of x is f of x over g of x. All right, so all of these are kind of like, yeah, I didn't really need you to come and write that on a board. I just kind of knew that already, right? What else would you mean, right? But composite is a little bit trickier. So here's the way that works. F composed with g of x is equal to f of g of x. And just to give you context here, g composed with f of x would be different. See, g composed with f of x would be g of f of x. And those don't have to be the same. Right? Those don't have to be the same. Contrast that with this, f of x times g of x, right? Those are just numbers, whatever they are. So you can commute numbers, right? F of x times g of x is equal to g of x times f of x, yeah? But f of x, g of x times f of x is exactly what we would define to be the product of g times f of x. So f times g is equal to g times f. But f composed with g does not have to be equal to g composed with f. These are really, really different. Just like, it's also true for division, right? If you did g over f, what would that be? G of x over f of x, right? Those wouldn't be the same either, would they? So composite is more like division than it's like multiplication, right? There's a difference between one way or the other. It doesn't commute. Let's see here. What example was I on? 6? All right. Let's look at f of x equal to, oh, I don't know, 3 plus 1 over x, and g of x equals to x squared plus 1. Let's calculate all of these things for these two functions, right? Let's find the formula. Find the formula for these functions, for the new functions, all right? So let's do it. F plus g of x, what is it equal to? 3 plus 1 over x plus x squared plus 1. There you go. Of course, we could simplify it, right? 3 plus 1 is what? 4. I mean, like if a student left it like this, I'd just be like, wow, that's lazy. But, I mean, sometimes I respect being lazy, but I mean, I think we can add 3 and 1. That's not too much. We didn't break our brain doing that, right? So you need a calculator. There's a famous professor at NC State where I went to undergraduate at NC State, and there's this guy who So long before people were taking selfies, like he took a picture of himself with like a digital camera, and that was his picture. I mean, he was doing that like 15 years before it became popular to like kill yourself doing that. And I mean, I guess those are accidents, but anyway, he would teach calculus, and he would tell them in calculus, he'd be like, if I meet you in the hall later, and I ask you, what's the fundamental theorem of calculus? And you say, I don't know. He's like, I kill you. It's just, I feel like maybe adding 3 and 1 on a calculator, I'd be like, I kill you. I don't know. You should, anyway, I don't know. Oh, okay, I digress. So 3 plus 1 over x minus, and then parentheses are your friend, x squared plus 1, right? The minus goes with both of those. Yeah? So we get what? I can simplify this. We got 1 over x minus x squared, and what's my number? 3 minus 1 plus 2. I mean, you might be like, why did you write those in that order? I don't know. It's just what happened. A constant times f. You guys pick the constant you want. What constant do you want? 4. All right, so 4 times f of x, what would that be? Technically 4f of x would be 4 times 3 plus 1 over x, which would be 12 plus 4 over x. So there's 3 times the function's formula. Let's see here. The product, fg of x, how's that go? So we go 3 plus 1 over x, right, times x squared plus 1. I'm not going to multiply that out. That's not really the point here, all right? That is it right there. That's the formula for fg of x. Notice that this is equal to x squared plus 1 times 3 plus 1 over x, right? So just to illustrate once more, this is the product of two functions. F times g is g times f. They're equal. The product of two functions are equal. Whether or not you order, whatever you order the product, first then the second, or the second times the first. F over g is what? F over g. So we have f of x over g of x. What's that look like? 3 plus 1 over x over x squared plus 1. That's the quotient of f by g. What would g over f look like? Pretty much the same thing, but yeah, the reciprocal, exactly. And of course, we could simplify these by multiplying through by x and making it a simple fraction rather than a complex fraction if you wanted, but I'm just really trying to communicate to you how these things work here at the moment. Okay, finally the point that there's some danger here. F composed with g of x, how's that work? So the way that works is that this is f of g of x. What is g of x though? G of x is x squared plus 1, right? And so I have to put x squared plus 1 into the formula for f. Right? So what I have to do is I do 3 plus 1 over parentheses x squared plus 1. That's f composed with g of x. Let me do the other way. So g composed with f of x would be g of f of x. Here f of x is 3 plus 1 over x. Right? So now I need to take 3 plus 1 over x and put it into the formula for g, which means I square the input and I add 1. So I have to take parentheses 3 plus 1 over x, take that thing, square it, and add 1. It should be pretty obvious that f composed with g of x and g composed with f of x are not equal, right? Is this equal to that? I mean, pretty clearly no, right? So everyone here comfortable with what I just did in terms of composition? Surely there must be somebody here who feels a little bit ill at ease with like that calculation, like maybe you didn't quite follow it. This is the thing people have trouble with, composition. Let me show you another trick for doing this calculation. It's just a little notational trick that might make it easier for you. If for whatever reason you couldn't follow, if you didn't quite see what I did, you know? So alternate notation. So kind of a trick notation for composition, let's say. So, okay, so still sticking with my example 6, all right? So let's look at f composed with g of x, all right? I can think of that as f of g. And just think of g as equal to g of x, right? Where g of x was what, x squared plus 1, right? Fine. What would f of g mean? That just means that you take the formula for f, right? And put g in the place of x. So we get 3 plus 1 over g. That's an easy step, right? And then I take that and I put in what g of x is. Maybe that makes more sense to you than me just doing it down here, right? G composed with f, how's this work? So I think of that as g of f, where f is equal to f of x, you know? Which, by the way, is 3 plus 1 over x. So what does g of f mean? Well, that should mean I take x and replace it with f, right? So that's f squared plus 1, yeah? See it? And then I make the substitution, f of x is equal to 3 plus 1 over x. So if you have trouble with composition, you can use this substitution idea to get out of trouble. If you learn this carefully, you can always do the substitutions. I would say this is the, maybe you call this the method of substitution or something. I don't know. It doesn't have a name that I know of. Any questions? So, the final example for today. What if instead of having formulas, you just have numbers? All right, you just have numbers. So like example, what am I on, 9, 8, 7, okay. Suppose you know f of 2 equals 6, g of 2 equals 7, and let's say f of 7 equals to 11. So if that's all the information you have, you don't have formulas, right? You just know these values. You can still calculate things, right? For example, f plus g of 2. You can do f minus g of 2, right? You can do f times g of 2. And finally, we can either do f composed with g of 2, or we can do g composed with f of 2. Let's figure out which. So let me do the easy part. F plus g of 2 is what? It's f of 2 plus g of 2, right? Which is 6 plus 7, so you got 13. Great. F minus g is 6 minus 7, so you got minus 1. F times g of 2 would be f of 2 times g of 2, 6 times 7, 42. Answered everything right there. F composed with g of 2, that's f of g of 2. What is that? F of g of 2, or g of f of 2 for the next one. So f of g of 2 is f of 7. G of f of 2 is g of 6. So what is f of 7? Well, we happen to be given that that's what? 11, right? So the answer here is 11. G of 6, what is g of 6? The answer is we don't know, right? We're not given enough information to answer that question. So in order to finish this, you guys have to tell me what the value of 6 is. 6 is for g. You can make it whatever you want. What do you want? G of 6 is equal to what?
5.
5? All right, we have a 5. So that makes the answer 5. And that's it. Now there's one other way you can ask these kind of questions, which is to give you guys a graph, and then you can read information of the values of the function off the graph. But that's all we have time for today. So next time I'm probably talking about parabolas. Yep.
So if that problem comes up like that where you don't give us that information, we just make up whatever number we want?
No, then you should say, Dr. Cook, did you do something wrong with this test? Like, did you get a chance to work this test out before you gave it to your students? Like, or is this just